So let's take a look at first section in chapter 2. Okay. Chapter 2, pretty much the whole chapter is going to focus on polynomials. We'll talk about polynomials. Okay, so this is a degree 3 polynomial. Okay. All that means is the highest exponent in it is a 3. Okay. And this highest exponent tells us a lot of things. It tells us how many times the graph can turn. Okay. A polynomial turns one less time than its highest exponent. So in this case, it could turn up to 2 times. So let's graph it, and let's see how many times it crosses the x-axis. Okay, just because it can turn 2 times, up to 2 times, doesn't mean it has to. Maybe this one does, maybe it doesn't. Okay, so on y equals, type in that equation. 2x cubed minus 3x squared minus 3x plus 2. And keep in mind, we're going to look for maybe some behavior that could go off the screen. Okay, and if it does, we'll change the window. But let's just start with zoom 6. Actually, I think that window is fine. Okay, Dave, how many times does it look like that graph crosses the x-axis?
3.
Yeah, it crosses 3 times. Okay. Looks like somewhere around -1, maybe +2, and then maybe a half. We could find what those values are if we wanted, but let's just answer this question. Crosses 3 times. Okay. What's the y-coordinate anywhere that a graph crosses the x-axis? Yeah, 0. Okay, if you're trying to find where something crosses the x-axis, you're setting y equal to 0, and you're solving. Or in this case, f of x. Now, let's show that this is basically a factorization of the polynomial I just had. Let's show that this is exactly the same as what I have up above. Okay. How could I do that? Okay, one way I could do it is graph it. Now, graphing doesn't prove it's the same. They might look extremely similar. Okay, and chances are if you graph 2 things, and the lines are right on top of each other, they're probably the same. But the only way to really prove that this is the same is to do it out. You'd have to do out the algebra and see what you get. Okay, so let's just do it out real quick, see what we get. So I'm going to FOIL the first 2, and I get 2x squared minus x plus 2x minus 1. Okay, combine our like terms. We're going to get 2x squared plus x minus 1. And distribute it out one more time. All right, so we get 2x cubed. We're going to get x squared. We'll get minus x. We'll get minus 2x squared. Minus 2x. Whoops. I'm sorry, that should be -2 times +2. That's -4. Sorry about that. -2 times x is -2x. And -2 times -1 is +2. Okay, let's combine those like terms and hopefully get what we have up above. 2x cubed. So that's that. We have x squared, take away 4x squared. That's minus 3x squared. That's good. We have a -x and a -2x. That's a -3x. That's also good. And we have a +2. Perfect. So we just showed that this factorization is exactly the same as what I graphed originally. Okay. later on, you'll learn how to factor this, okay, and get this as your answer. Well, not today, but as we go through the class, you'll learn how to do that. Right, now let's go ahead and find the exact solutions. Okay, on the calculators, anybody remember under second calc what you can use to find the x-intercepts of this graph? Yeah, the zeros. Okay, and because there's three of them, you've got to be careful about your left and your right bound. Okay, so if I start at the one furthest to the left, pick a point to the left, see how it puts in the dotted line? Pick a point to the right, now it's going to look between those dotted lines. Okay, do a guess, and it tells us one of the answers is -1. Now if you go through and do second calculate 0 for the other one, you'll get 1/2. Okay, you could try it, but you will. And anybody know what you're going to get for the very last one?
2.
Yeah, you do get 2. Now we found those answers graphically, but look at what happens if you plug each one of these numbers in to this factorization up here. If you plug in -1, what's -1 plus 1? And 0. And 0 times anything is what? 0. So just by looking at what makes this first factor 0, you could have figured that number out. Look what happens if you plug in 1/2. 2 times 1/2 is 1. 1 take away 1, 0. 0 times anything, 0. The last one, if you fill in 2, 2 minus 2 is 0. So the point here is, if you can factor something, you can find the roots very quickly, just by figuring out what makes this 0, what makes that 0, and what makes that 0. But we have to learn how to do that factoring. For now, we'll probably stick with using the graphing calculator. It's a nice way to double check our answer. So any questions how we got those 3 answers on the calculator? Right, so there's a lot of names for those answers we just found. They are x-intercepts. You can call them that. They're called roots of an equation. They're also called zeros. In fact, if you use an older graphing calculator, I think the TI-82. In fact, let me bring that up. So if I put this on an 82, and I go to second calc, see, it doesn't call it a 0. It calls it a root. So older calculators actually used this different name. Okay, but they all mean the same thing. Root, 0, x-intercept. It's basically the number that you plug in that would make y 0. And in this particular equation, there were 3. Also, think back to the highest exponent in that thing we just graphed. It was a 3. Highest exponent was a 3. 3 solutions. Okay, that's not just a coincidence. That exponent doesn't, the highest exponent doesn't always guarantee that there's that many solutions, but there won't be more than that. Okay? It's possible you could have 2 or 1 in the type of problem we just did. So if you have a linear equation in the form ax plus b equals 0, it's kind of like y equals mx plus b. Okay, and you want to know what the x-intercept is? It's very, very simple. All you got to do is subtract b and divide by a. Right, so you just bring the constant to the other side, divide by the coefficient of x. And that will tell you what value you'd plug in for x to make y 0. Okay, nice thing about a linear equation, it's very easy to solve. Super easy to get x by itself. Even a quadratic, we can still solve it using the quadratic formula if you have to. Once you get above quadratics, unless you can factor it, there's no guarantee that there's going to be an easy way to solve it. All right, so when we start solving things like Cubix and 4th and 5th degree polynomials, I have to give you special problems that factor nicely. If I don't, there's no such thing as like a cubic. Well, actually, there is a cubic formula. It's the one above a quadratic formula, but it's extremely long, so we don't use it. Okay, so I'll always give you problems that have like a trick to them. It makes it easy to factor. All right, so here I've got the equation 2x plus 3 equals 0. Since I'm setting it equal to 0, all I want to really know is the root. What's the root in this problem? Yep, Aiden? Negative 3 halves. If you plug that in for x, you'll get 0 for y. Good. Okay, questions on that? All right, so that was a linear equation. We're not going to spend any more time on linear. Okay, that's really algebra 1 stuff. Okay, so let's step up to a quadratic. Okay, at this point, we should all know what a quadratic looks like when you graph it. How many roots can a quadratic have? What are the possibilities? Pardon?
0, 1, and 2.
Right, 0, 1, or 2. It's a U shape, and depending on how you sketch it, that U shape could cross the x-axis twice, once, or not at all. Okay. Does anyone remember how the discriminant can tell us whether we have 0, 1, or 2 solutions? There were three cases. You remember what you're looking for when if you do b squared minus 4ac. There's 3 things that it could come out to. Yep.
Comes out negative.
Yep, if it comes out negative, what happens there?
There are no solutions.
No solutions. At least, no real solutions. We'll talk about imaginaries later. Okay, so if it comes out negative, no real solutions, wouldn't cross the x-axis. Okay, what else can happen? Yeah?
It comes out to exactly 0. That's 1.
Comes out to exactly 0, you get 1 solution. And anybody else give me the last case? John?
If it's above 0, like positive, then you get 2 solutions.
Yep, if b squared minus 4ac comes out positive, you get 2 solutions. Okay, we talked about that, I think, towards the end of the notes at some point this week. Okay. Try to solve this one. Okay, what's the first thing you want to try to do anytime you're solving a quadratic? This is not really set up the way it should be. Some stuff needs to move around. Yeah?
So
Don?
one side's 0.
Yeah, let's set one side to 0. Can you tell me what it would be if you moved everything to the left-hand side?
2x squared plus 2x minus 1.
Good. Okay, now that's, I don't think that's going to factor. Okay, if you tried, really the only thing you can try here, which I don't think is going to work, you've got to have plus and you've got to have minus, right? Because you've got to get a negative constant. And there's only 2 numbers you can multiply to get 1 that are integers, 1 and 1. That's not going to give me the middle. Okay, so this isn't factorable. So how else could we solve it besides factoring? I wrote approximate, and I am going to do that after, but we haven't practiced this yet fully in this class, so I think we should.
Quadratic?
Yeah, let's use the quadratic formula. Okay, so A is 2, B is 2, C is negative 1. Okay, we're going to fill in our quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, what I'm going to do right away, since I have minus a minus, those are going to cancel each other out and become positive. All right, and I get negative 2 plus or minus the square root of 4 times 2 is 8. 8 times 1 is 8. 4 plus 8 is 12. And we were expecting a number we couldn't take the square root of, because if we got a nice integer answer here, we probably would have been able to factor it. Okay. And how do you reduce the square root of 12? Yep.
2 square roots of 3.
2 square roots of 3. Good. Okay, so you write the square root of 12 is one way to do it, is write it as square root 4, square root of 3. And the square root of 4 is 2. Square roots of 3. Okay, so there's your exact answer. Quadratic formula is the only way to get the exact answer. If you wanted it approximate, use the calculator. Now, there's 2 ways you can solve it. One way you can solve it is type it in just the way it is. Okay? Put 2x squared. Put that in y1. Put 1 minus 2x in y2. And we're going to try to find where these 2 pictures are equal. What does that really mean? That's kind of a weird way to say it. Where 2 pictures are equal? Yeah.
They intersect.
Yeah, I'm going to find where they intersect. Okay, so do zoom 6. There's your parabola. There's your line. Notice there's 2 spots where they intersect. Okay, I'm going to grab the one on the left-hand side. If somebody else can get the one that's towards the right, it'll save us a little time. So the one on the left is negative 1.37. Okay, about. And I'm sure if you typed all this into a calculator, that would be one of the answers you'd get. And how about the other answer that's more towards the right? Yeah, go ahead, Leon.
0.37.
0.37? Okay, thank you. Now, if you didn't want to type it in and do an intersect, you could do this step. Okay, I could type it in this way. And if I typed it in as, let's see, 2x squared plus 2x minus 1. Okay, just watch this part. 2x squared, is it minus, plus 2x minus 1. Plus 2x minus 1. What am I looking for now? I'm not looking for an intersect now. I'm looking for something else. Yeah, I'm not looking for where they intersect. Sorry, I'm not looking for where graphs cross. I'm looking for the x-intercept. I can do it either way. And now if you do second calc 0, you're going to get exactly the same answers that we just did, graphing it the other way. I'll just find the same one again. Negative 1.37. Right? So a lot of problems that ask you to find an intercept or a root, you can either do a y1 and a y2 and see where they cross, or move everything to one side, get it equal to 0, and do a second calc root, or second calc 0 on a new calculator. Any questions about doing that either way? Both ways are fine. All right, this part, just watch me read this off. You don't have to write this down. You're going to see this in the book, though, and I just want you to be aware of it. This book was written before they had second calc root, or second calc 0. So what they used to have to do is basically keep zooming in, okay, on the point, so you got closer and closer and closer, and then trace to try to get as close as you could. Right? And then they'd zoom in again and keep tracing. We don't need to do that anymore. Okay, there's no reason to repeatedly zoom in. because now we have this second calc feature. Finds it automatically. All right? So in the book, when they say find a root with a maximum error of 0.01, that basically just means round it to the nearest hundredth. A lot of people get confused by those directions. Okay? So find the root with a maximum error of 0.01 just means round to the nearest hundredth. Okay? And don't worry about doing this zoom thing the way they suggest. Just do it the way I showed you. Second calc 0. Okay? Questions on that? Okay, just that's for an older calculator. Okay, so better method I already have shown you. Use second calc. All right, and let's try this one. Okay, this is a cubic. We don't have a formula to solve it exact, so we're going to have to graph it. We actually could do some factoring here. Since they both have an x, we could factor an x out and make it into a quadratic. But it just says to solve approximately. All right, so Jacob, how do you want to do this one? Do you want to do this one just the way it is and see where two things cross? We want to bring everything to one side.
0 from one side.
You want to put it on one side?
Yeah.
All right. So you have x cubed plus 2x. What would be on the other side there?
-1.
-1. Okay, so he chose to move everything to one side. So that changes how we're going to do it a little bit. Okay, hit graph. Oh,
I have. Okay. Where did you get that?
thank you. X cubed plus 2x minus 1. That's going to make a big difference. Okay, I'm probably going to have to zoom out. Actually, I can kind of see what's happening right there, but let's just do zoom 6. Okay, so I said a cubic can turn up to 2 times. This one really doesn't. It kind of thinks about starting to turn a little and then turns, but it goes back up. But it never really does something like this. Never really makes a full turn. Just kind of thinks about it and then just keeps going. All right, so how about Jen? Tell me how I get the root here. What do I press?
Second calc. And then 0.
Yep. Now what?
Just click to the left of it.
Yeah, I'm already to the left of it, so that's fine. Yep.
And then go to the right.
Okay, make sure we go to the right of it. Anything else?
You can just click again.
Yeah, I could just click again because it's not like I'm looking for 2 roots that are very, very close. There's only 1 root in those dotted lines. It'll find it. Okay, 0.45. Do people get 0.45? Yep. Got an error? Okay, make sure you press second calc. Make sure you're using root or 0. Yep. Make sure you're definitely to the left, so your y value should be negative. Okay, then make sure you're to the right, so your y value is positive. And then the guess, just pick a point somewhere in the middle. Anybody else getting an error on that? You got it?
Yeah, I was putting my left thumb to the right and then
Okay. All right, so that was quadratics. Okay, let's take a look at a 3rd degree polynomial. Okay, 3rd degree polynomial has this form. Okay, A, B, C, and D can be any real numbers you want, except A can't be 0, because if you make A 0, you'd wipe out the first term. Now you don't have a cubic anymore. Yep, back down to a 2nd degree, quadratic. Okay, so A, B, and C, A, B, C, D, any real numbers except A can't be 0. Okay, Okay, page 80 shows all the different types of cubics that you can have. Okay, we've already seen some of them. Okay, we've seen the kind of cubics that actually do those turns and come up. Okay, the one on the left here is always increasing. The one on the right, it's always decreasing. Okay, same thing with the other two. The one on the left. Okay, it's mostly increasing, but actually goes down for a little bit, but then it goes right back up. Okay, and the one on the right, it's decreasing most of the time, except in this very small area. It does start to go back up, but then it just keeps going down again. Okay, so those are the different types of third-degree polynomials. Okay, this one, it's just asking me how many solutions does that equation have. I don't actually have to find them. That could be another question later on. But for now, just tell me how many solutions that has. So take a second and try to graph that. Do you think you have it, Aiden?
Yeah.
Just hold on one. Yeah, just give people another second. Just to, looks like most people have it though. Yeah, go ahead, Aiden. What'd you get? How many?
3.
Okay, let's look at it. So we're looking for where it equals 0. We're looking for how many times does it cross the x-axis. Yeah, that one's pretty clear. You don't even need to zoom in and look. It's pretty clear it crosses 3 times. Okay, and eventually what we'll start doing is describing what's called the end behavior of the polynomial, meaning if you look at the left side of it, what's happening? Well, on the left side, it's heading down forever. On the right side, it's going to keep heading up forever. So a lot of times we'll use, I'll show you a notation later on to describe that. Okay, now the next example connects in with example 5. Find the middle root. Okay, by middle, I mean that one right there. So we find that middle root. Let's give people just a second to type it in. Okay, go ahead, Dominic, what'd you get?
Approximately 1.55.
Let's see, yep, about 1.55. Okay, how many people got 1.55? Okay. Anybody having trouble? They weren't able to get 1.55? That's good. Okay. All right, so that's it for section 2.1. Okay, that one's pretty short. All right, 2.2, a lot of this is going to be on the calculator. We're not going to get to the whole thing today. Okay, we'll do part of it. Okay, and the focus of this section, there are going to be some word problems. Hopefully you already can solve them with the skills you already know from Algebra 1 and 2. The idea is more on graphing the solutions. Right, so anytime we solve some kind of mathematical word problem, part of the solution usually involves making either an equation or a graph. Okay, a lot of times, especially in Algebra 1, you're just making an equation and you're trying to solve it. Okay, an equation, that's an algebraic representation of a problem. A picture, that's more of a graphical representation of a problem. Okay, and in pre-cal, we combine both approaches. Sometimes we'll make an equation, and then we'll use the calculator to solve it. So kind of do both things together. Okay, let's look at this problem. This is one that we're going to do exactly that approach. We're going to try to come up with an equation first. And we could solve it with algebra, but I think more people are still getting used to the calculator, so we'll probably do it that way. If there's any formulas you need to know having to do with interest or investing that I haven't given to you, I don't expect you to know them. Okay, I'll give you any formulas that are not something, if you haven't learned it, I'll give it to you. Okay? All right, so Bill's going to invest $20,000. He's going to invest part of his money at 6 3/4% simple interest, and the remainder of his money is going to be invested at 8.6% simple interest. Okay, so if you don't know the formula for simple interest, I'm going to give that to you. It's I equals PRT. It's a simplified way to calculate interest. A lot of banks don't do it this way. They do something called compound interest. But to simplify the problem, I don't want to get into that. Okay, and in that formula, there's 4 variables. I is the amount of interest that you make. P is your principal, or how much money you're investing. R is the rate that you're investing the money at. Remember, rates always have to be as a decimal. So if you had like 5%, that's 0.05. And T is the time.
Is that in years, seconds, minutes?
Generally, it'll be in years. Yeah. So we're going to try to find an algebraic representation for how much interest Bill's going to earn in 1 year. And I'll give you a hint. Let's assume, we'll use x as our variable, and assume that he invests x dollars at 6.75%. And then if he has $20,000 and he's already invested that much of it, we can figure out how much is left for the other investment. Okay, so let's start just by figuring out how much interest he's going to earn on the 6 3/4%. Okay, first thing we need is the principal. How much money is Bill going to invest at 6.75%? Well, $20,000 is his total, but only part of that is going to go into the 6.75. Right, we don't know a number, but we do have something that represents it. Yeah. Assume he's going to invest X dollars at 6.75%. So that's the principal. Okay. What's the rate? It is 6.75%.
That's 0.0675.
0.0675. Good. Times the time. Okay. How long is he investing the money for? 1 year, so we actually don't even need the 1, but we'll put it in. Okay. So that's how much interest he's going to earn at 6.75. Now let's find out how much interest he's going to earn at 8.6%. How much money is he going to invest at 8.6? Right, he had 20,000 minus what he already has invested in the other investment. Okay, the rate, I'm going to change it to a decimal, 0.086. Again, the time is 1 year. We don't really need that. Now, how would we find the total interest? What would we do with each one of these? Add them together, because he's making interest from both. Okay, so add them up. Okay, so his total interest, I'm going to write this a little nicer. I'm going to put the number in front like it's a coefficient. So we'll call this the total interest. It's 0.0675x plus, and if I want, I could distribute out the 0.086 and then I'll have some like terms I can combine. Right, so I've got minus, let's see. So it's actually going to be a minus, I'm just putting my like terms together, 0.086x. And then 0.086 times 20,000.
172.
What is it?
172.
172, thank you.
Oh, 1720. There's a 0 there.
What is it?
1720.
1720. All right, so I just distributed this out, and now I'm just going to combine my like terms. Does anybody have 0.0675x minus 0.086x?
Negative
-0.0185 plus 1720. Okay. So there's our algebraic representation of how much interest he's going to earn in 1 year. Okay, didn't say anything about graphing it yet. I think that's going to be the next part. Yeah, we'll do that in the next part. Right, so as we graph this, we want to keep in mind the difference between a complete graph, okay, which is basically you have to see all the different features and characteristics of the graph, versus a window that just shows you what makes sense in your problem. All right, so a lot of times when we do that, we cut some things off. Okay, a lot of times when we have a real word problem, we cut negatives off. If we're talking about time, usually negative doesn't make sense. If we're talking about money, sometimes negative doesn't make sense. It depends on the problem. Okay, but just keep in mind what your window should be here. Right, so before we even do part 2, let's just get the graph from part 1 up. So we've got negative 0.0185x. Plus 1720. All right, so I know I have a y-intercept at 1,720, and the slope is negative, so it's going to be heading down very slowly from 1720. Now I know Bill's not going to lose money, so I shouldn't look at negative interest. And I also don't need to look at negative amounts of money. Okay, so I would set my x min and y min both at 0. Okay, y max. I know I don't really need to go higher than 1720 because I saw my y-intercept. And x max. What's the highest value that would make sense here? Remember, x is how much money he's investing. Yep.
20,000.
20,000. You wouldn't want to go to 30,000. He doesn't have 30,000 to invest. 20,000 is going to be as high as we can go. Okay, so that represents all the different values of interest that he could make. Okay? So remember, X is how much money he invests at 6 3/4%. So if he were to invest $10,000 at 6 3/4%, the other remainder, in this case 10,000, at the other amount, he'd make $1,535. Okay, notice the more money that he invests at the lower interest rate, the more money that he puts in the lower interest rate, the less and less interest he's making. Okay? His best option would be don't invest anything at 6 3/4%, put all the money in the higher interest rate, and then he'll make more interest. Okay? The reason why he might not want to do that, maybe there's some risk associated with this one. If this was like a stock market, maybe he could lose money. So maybe it's good to put some money in like a conservative area, even though you might not make as much, and then gamble with something, you could make more money, but maybe you could lose money. Okay, we don't know all the details to this problem. Okay, but what we want to figure out is how much money did Bill invest at each rate if he earned that much in interest. Okay, how would I use the calculator to figure that out? What would I do? So you're basically plugging something in on that side. Derek?
You would put in y equals $50
Okay.
Then you find where the intercept.
And find where they intersect. So basically all you're doing is plugging in $1,509.10 on the left, and you're solving for x. Okay, algebraically you could do it, or let's just do it graphically. It's $11,400. So he invests $11,400 at the 6 3/4%. Okay, and the remainder, well, he had $20,000. He already invested that much, so he's got $8,600 to put in the other account. Any questions on how we did that? Yeah.
Wait, how did he get the 11,400 for 6.75?
So I graphed the original equation. I graphed what Derek told me to put in y2, and then I found where they intersect. Yeah. You could accomplish exactly the same thing as if you put this here, and then subtracted 1720, and then divided by negative 0.0185. You get the same answer. Just graphical versus algebraic. Okay, any other questions on that one? Okay. So this will be our last one. In fact, I think we might have already done this. It says, consider all rectangles with a perimeter of 100. Find an algebraic representation that describes the area. Was that one from a homework?
Yeah.
Yeah. So I think we already
Oh, come.
we already did it. So let's just we'll go through it quick again. Okay, what would be my first step here? Since we've already done it once.
Mark the sides, and mark.
Well, remember, how many variables did I use when I did it? Just one. So we're going to use one variable. You want to start with L or W?
L.
Okay. So length.
And the size could be just
50 minus L. 1 minus 2 L, or 50 L, so.
divided by 2.
Right. So you've got 100, think of it, you've got 100 feet of material to use up. You've already used up L for the top and L for the bottom. So if that's how much material you have left, you have to divide it by 2, because half the material is going to go on the left-hand side, half's going to go on the right. I think somebody just said, how much is that? 50 minus L. Okay, and now we're trying to find an area. So what do you do with length and width to find an area in a rectangle? Length times width. So in this case, our area as a function of the length is going to be L times 50 minus L. And what kind of equation would that be if you distribute it out? Or what degree polynomial? Tell me.
Wait, what degree?
Yeah.
Second.
Yeah, it's a second degree or it's a quadratic. Okay, it would be negative L squared plus 50L. Okay, so either answer is fine. And the last step, find a complete graph of that equation. Okay, what kind of values don't make sense here? Want to make sure we don't use those. Yeah, we don't want to use negatives. We're not going to have negative length. And negative also doesn't make sense for area. We're not going to have negative area. All right, so that's fine. We already got the negative set. My maximum area, I think we already know. We tried about 700 before. And really, I can't go any bigger than what number for L? You can't even go as high as 100. Like if you did 100 and 100, that'd be too much. Yeah, it's like 49.9. You can't go to 50. Because if you use 50 on the top, 50 on the bottom, now you have nothing left for the sides. Okay, so you can't go really any bigger than 50. That's going to fill the whole screen. Perfect. Find a complete graph. Okay, so on the homework, if they ask you to do that, just write down your window. X min, X max, Y min, Y max. And I think we already calculated it was a square, 25 by 25. Okay, any questions on section 2.2 part 1? All right, so the homework will be on 2 pages. Okay, this will be due next time I see you guys. So you guys are in shop next week. I'll see you on the 14th, Monday. Okay, so page 82, 1 through 5, 8 through 11, 15, 27, 28, 31, 34, 40, and 45. Okay, that's section 2.1. And then what we did from 2.2, 5 through 12, 21 to 23, and 31 through 34.